In this video, we're going to be proving this weird inequality involving a bunch of powers of root 2. So we've got root 2 to the root 2 to the root 2 to the root 2, all the way up to the root 2, 20 square root of 2's here. And our goal is to show that it's between 1.999 and 2. Of course, you're not allowed to use a calculator because that would make it not so fun. Plus, it would take a while to type in even with a calculator. So I don't want to do that. I'm going to use my brain instead of my calculator. Okay, so first of all, proving that this is less than 2 is actually relatively simple. So what we can do, just to make things easier to write down, is we'll introduce some notation for this. So we'll say an is root 2 to the root 2 n times. Okay, so our goal is to show that a20 is between 1.999 and 2. So just show that it's less than 2, we can basically just proceed by induction. So certainly a1, which is just root 2, is less than 2. So
I can write an plus 1 equals root 2 to the an.
so if an is less than 2, then this will be less than root 2 squared, which is 2. Okay, so all of these terms will be less than 2. Doesn't matter how many times you repeat this. In fact, the limiting value is equal to 2, but you'll never quite reach it without going infinitely far. Now, the other part is much trickier. For that, we need a good estimate on how fast these aons are growing. So to do that, what we could do is look at how far these aons are from 2 and look at those differences. So again, I'm going to introduce a little bit of notation. So let's say dn is 2 minus an. Okay, so this is just how far away an is from 2. And our goal is to figure out how small d20 is. So the difference between a20 and 2. Okay, so what I'm going to do is find a recursion for dn and then use that to estimate d20. So our goal here is we want less than 0.001. And that way we'll show that an is bigger than 1.999. Okay, so this looks intimidating, but let's just go for it. So I already have this recursion for an. So I'm going to use that to get a recursion for dn. Okay, so what I get is 2 minus dn. It's the same thing. Okay, so let me just plug that into this equation here.
And that gives me 2 minus dn plus 1 equals root 2 to the 2 minus dn.
Okay, so it's not a very pretty recursion, but let's see what we can do with that. Well, I can solve for dn plus 1 here. So dn plus 1 will be 2 minus this thing on the right. And now root 2 squared is just 2. So let me take that out.
I'll get 2 minus 2 times root 2 to the minus dn.
And I'll factor out the 2. Okay, so dn plus 1 is this mess here. Now, the nice thing is that dn is going to be small. Even d1, so that's the difference between first term and 2. The first term is root 2, so 2 minus root 2, that's about 0.6. So these terms are all going to be at most around 0.6. Okay, so I can use the Taylor series to expand root 2 to the minus dn to estimate how big that is. So let me just expand that. So, well, this is e to the 1/2 natural log 2, well, minus Okay, now I know the power series for e to the x. So that will give me, it's going to get a bit messy.
So when I use the Taylor series of e to the x, I get 1 minus a half log 2 dn plus a half log 2 squared dn squared over 2 factorial.
Okay, and the terms get messier. But that's all I need, actually. Because, well, the ones drop out.
So I'll get 2 times a half log 2 dn minus an eighth log 2 squared dn squared, and so on.
Now, the nice thing is that, well, these terms are alternating in sign, but they're decreasing rapidly in absolute value. So in fact, this will always be less than just the first term. Now, equivalently, you could say that 1 minus e to the minus x is always less than x. With this estimate, what we end up with is, well, remember this was our dn plus 1 on the left. So we get, and this 2 combines with 1/2. So we get dn plus 1 is less than log 2. Yeah. Okay, so let's just recap what we've proved here. We've proved that the difference between this power tower and 2 decreases exponentially fast. So each time you get something less than log 2 times the previous thing. Now, for our purposes, we won't need a very good estimate on log 2. It's about 0.69. So let's just say this is less than 0.7. And remember, d1 was 2 minus root 2, which is less than 0.6. So altogether, what we end up with is dn is less than 0.6 times 0.7 to the n minus 1. Or if you want, you can make it even less precise and say it's less than 0.7 to the n. Okay, 0.7 to the n is a bit hard to estimate, but fortunately, if you square it, you get 0.49, which is pretty close to a half. It's less than a half.
So we get dn is less than a half to the power n over 2.
So what we've shown is this whole thing is, well, it's positive, but it's less than 1/2. Okay, and now remember, we wanted to look at what happened when n was 20. Now when we plug in n equals 20,
we find that the difference is less than 1/2 to the 10th, which is 1 over 1024.
and that's less than 0.001. So indeed, the difference between the 20th tower and 2 is less than 0.001, and that shows what we wanted to prove. It shows that the tower lies between 1.999 and 2. And this inequality is actually pretty good because this tower doesn't cross 1.999 until 18 root 2s. So we're only off by a little bit. And the estimate will get better and better as you take more and more terms, because then the power series we're using to estimate the differences will become more and more accurate as these dn decrease.